Well, continuing from the previous part two, we'll look now at calculating the transmission and reflection coefficients from those previous results. Remember that toward the end of part two, we got that the reflection amplitude B ratio to the incident amplitude is given by the top expression here. And the transmission amplitude to the incident amplitude is this expression where this dimensionless parameter beta is mv naught over h bar squared, h bar squared times k. And like we've done before, we can now compute the reflection and transmission coefficients. Reflection coefficient is just J reflected over J incident, and we have had expressions for those. It's calculated exactly the same way as we did earlier for the J's, which is the probability current densities. For the reflection, it's just h bar k over m times the amplitude b squared. And for the incident wave function, it's h bar k over m times absolute modulus of a. And I can combine those to b over a. And similarly with the transmission coefficients here. It's just simply by definition the ratio of J transmitted to J incident. And again, we calculated these in earlier lectures from the probability current densities as h bar k over m and h bar times the amplitude squared, and h bar k over m times the amplitude squared for the incident and reflected and transmitted waves respectively. And again, that can be reduced to simply this ratio absolute modulus squared. And then we can calculate them. We just plug in what our expression was for b over a minus I beta plus 1 plus I beta. And it's just that absolute modulus squared. Remember, it's a complex number, so I have to compute this, I have to compute the complex conjugate of it times the value itself. And the complex conjugate is just replace I by minus I everywhere. And then when I multiply these out, I get a real number. That's sort of the way they're designed. Similarly for the transmission coefficient, this transmission coefficient was 1, or the C over A was 1 plus over 1 over 1 plus I beta. And then when I take the absolute modulus squared of that, I get 1 plus beta squared. Notice I can do these two and add R and T. Got R beta squared over 1 plus beta squared and T 1 over 1 plus beta squared. So add those two up, and what you find is that it reduces to 1. And that's a general relationship that holds in general for any scattering process in one dimension. That R plus T, the reflection coefficient, plus the transmission coefficient, has to add up to be 1. You might say, why not just calculate T and then plug it in here and get R, and that's possible to do. But what I usually like to do is calculate R, calculate T, and then use this general relationship to check if I haven't made an algebraic error someplace, because I know they have to add up to be 1. Sometimes it's convenient to have these expressions in terms of the original energy and V naught. And if you recall, beta is mv naught h bar squared k, and k was the square root of 2m e over h bar squared. So if I square beta, I'll get m naught squared, v naught squared, h bar squared, which is h bar to the 4th, and then a k squared. But k squared is just 2m over h bar squared. And then that simplifies a little bit. One of the m's goes out, an h bar squared canceled, and beta squared simply becomes mv naught squared over 2h bar squared e. And if I plug those into r and t respectively, I get initially this and this. But most of the time when I look at this, I usually multiply top and bottom by E, the energy. That's the incident particle energy. And top and bottom here, and that gets rid of this E, puts an E instead of the 1, and gets rid of the E here, and likewise for the transmission coefficient. Those are a little bit easier to study in terms of some limiting cases, again, to check to make sure the results seem reasonable. As V naught goes to 0, so this would be the V naught and the delta function potential. So in that case, if V naught is 0, then 0 times the delta function is still 0, and so the potential is 0 everywhere. And so naturally you would expect if I have an incident beam or an incident wave, quantum mechanical wave, that there wouldn't be any reflection. And sure enough, as V naught goes to 0, the top becomes 0. And so R indeed goes to 0 like you would expect. And if there's nothing to scatter off of, well then the incident wave just continues on. And so all of the wave gets transmitted. And again, as I let V naught go to 0, then this simply becomes E over E, so that E goes to 1, or T goes to 1, and all of the wave gets transmitted. On the other hand, if V naught goes to infinity, well, let's look at the T term first. As V naught goes to infinity, remember E is the incident particle energy. That's what energy we're firing it into the collision initially, so we have really control over that. But it's a finite number. As V naught gets larger and larger and larger, in fact goes to infinity, then I get a constant over infinity, and T goes to 0. And likewise, as V naught goes to infinity, well, this constant E is negligible compared to an infinite term, so ultimately I can ignore that. And then the limit as V naught goes to infinity, I get that R is 1. So, and I guess that makes some sense too. If the potential becomes infinitely strong, well, one would expect even quantum mechanically to not have anything transmitted and have it reflected, all reflected. I'll also note that sometimes people like to have the reflection coefficient in the same kind of form, so they divide top and bottom by the numerator. And when you do that, you get reflection in this form, reflection coefficient in this form, and the transmission coefficient in this form. Notice these two terms. If this is beta squared, then this is 1 over beta squared. And the thing that's interesting about those two relations, as you can see most easily in this form anyway, is it doesn't really matter whether this is an attractive a delta function potential or if it's a repulsive delta function potential. So we worked it for the repulsive delta function potential where V naught was positive, but if V naught went to minus V naught to make it an attractive one, well, it only enters in these coefficients as V naught squared, and so you get the same reflection and transmission coefficients regardless of whether this scattering potential is attractive or repulsive, and that's kind of surprising to me anyway. You can check that. Your book goes in, I think, into some detail in the negative case, so be sure to do the readings out of your textbook and verify that you get these results. There's always some question, well, what's the physical interpretation of the reflection coefficient and the transmission coefficient? And basically they're probabilities. The reflection coefficient is the probability that if a particle is sent in, that it gets reflected. And the transmission is a coefficient is the probability that if a particle is sent in, that it will get transmitted to the other side. And so you can think of this also as if I send in n particles, and they have a probability of t of getting transmitted, well, then the probability times the number I've sent in will give me the number of particles that get transmitted. If I send in 100 particles, then t times 100 would be the number of particles that one would expect to measure coming through. And likewise, the number reflected, if you send in n particles, and r is the probability that any one of them gets reflected, then r times n is the number that one expects to come back at us in a reflected beam. So that kind of encapsulates this sort of probability, and somehow or another managed to write probability in two ways, neither one of which is the proper spelling. But in any event, I put these in quotes, the probability of reflection and the probability of transmission. And that kind of bears out this fundamental relationship of them as well, in which this is the r plus t, and obviously the sum of the probabilities have to be equal to 1. So